Welcome! In this video, we'll explore the intuition behind complex numbers in digital signal processing. First, we'll break down the theory in a simple, visual way. Then, we'll bring it to life with MATLAB code. Let's begin. To transmit data wirelessly, we rely on electromagnetic waves, which can be pictured as simple sine signals. But a pure sine on its own carries no information. To embed data, we need to shape the wave. The two key properties we can modify are its amplitude, that's the height or power of the wave, and phase, its position in the cycle. Before transmission, the two devices agree on a codebook, a mapping that links specific combinations of amplitude and phase to bit patterns. For example, an amplitude of 1 with a phase of 45 degrees might represent 0, 0. The same amplitude with a phase of 225 degrees could represent 0, 1, while an amplitude of 0.5 with phases of 315 degrees or 135 degrees could represent 1, 0 and 1, 1 respectively. When sending data, the transmitter slices the stream into chunks, here 2 bits at a time, and modulates the wave according to the codebook. The receiver, using the same codebook, observes the wave's changes and reconstructs the original bits. And now, here's the conceptual leap that powers modern communications. Instead of juggling two separate properties, amplitude and phase, we can represent each state as a single point on this 2D plane. And mathematically, a point on a 2D plane is perfectly described by a complex number. Think of it like this. The distance of the point from the origin, the absolute value of this complex number, gives us the amplitude. The angle the point makes with the axis, the angle of the complex number, gives us the phase shift. By just specifying these two simple numbers, I and Q, we are implicitly defining both the amplitude and the phase. This complex number becomes a complete instruction for the transmitter, telling it exactly how to shape the carrier wave. So how do we actually create this modulated wave? That's where the brilliance of the IQ modulator comes in. The transmitter takes our two numbers, I and Q, and sends them on two separate paths. The I component, the real part, is multiplied by a cosine wave. The Q component, the imaginary part, is multiplied by a negative sine wave. This is the same carrier, but shifted by 90 degrees. Finally, these two signals are added together. Thanks to trigonometry, their sum forms exactly the wave we wanted, one with the precise amplitude and phase set by our original complex number. This abstract IQ concept solved a real hardware problem. Rather than building complex phase and amplitude controllers, we use simple multiplications and addition, operations that are easy to implement in both analog circuits and digital processors. Now let's move on to the second part of the video, where we'll bring these two modulation methods to life through simulation. You can find the MATLAB code linked in the description below. We'll start by defining the parameters, beginning with the complex symbols. For this example, we'll use some simple, randomly chosen values. In real communication systems though, these symbols are carefully designed to minimize the chance of errors. If you'd like to learn more about that, check out our video on digital modulations. Next, we map bit patterns to these complex symbols and build a code word, a stream of bits that the transmitter will send. Finally, we visualize the result with a constellation diagram. As you can see, the plot shows 4 distinct points on the 2D complex plane, each representing a unique bit combination. Now, let's move on to signal modulation. First, we set a sampling frequency of 1000 Hz and create a 4-second time vector, 1 second for each transmitted symbol. Then, we map the code word bits to their corresponding complex symbols using the mapping defined earlier. The first method we'll demonstrate is manual phase shifting and amplitude scaling. For each symbol, we first select its time segment and calculate the phase shift based on the symbol's angle. Then we generate a cosine carrier and apply the calculated phase shift. Finally, we scale the carrier by the symbol's amplitude. This gives us a properly modulated segment, which we place into the overall transmitted signal. Next, let's look at the second method, which uses IQ modulation, the approach explained in the theory section. We define two carrier signals, a cosine wave for the I component and a negative sine wave for the Q component. To ensure the symbol and carrier vectors match in length, we repeat each transmitted symbol 1000 times. We then modulate by multiplying the I components, real parts, with the cosine carrier, and the Q components, imaginary parts, with the negative sine carrier, then add the two results together. Finally, we plot the outputs. As you can see, both methods produce identical waveforms. However, the second method is much easier to implement in hardware, which is why it's the standard approach in real communication systems. And that's it for this video. If you'd like to dive deeper into digital modulation, be sure to check out the next video. Thanks for watching, and see you in the next one.